good evening to you. And I was joking with everyone else, saying that I only signed up for this event because I can force people to listen to math. So you guys are here to listen to the math, so we'll go. So today's topic is on why numbers and polynomials are basically the same. And just to establish the ground, by numbers, I mean the integers, I mean the positive and the negative whole numbers. By polynomials, I mean the polynomials with complex coefficients. So, like, examples are here. X plus 1 is polynomial. 2x squared plus 3x plus root 2 of I is a polynomial. And I will show you that they are basically the same because they share two interesting properties. That is that you can do division with remainder and you can do prime factorization with them. And actually, it's logically linked in the sense that if you can do division with remainder, you can do prime factorization. Let's start with the integers. What is division with remainder in integers? It's called the Euclidean algorithm. Well, this is what you learned in second grade, that if you have... it's kind of what you learned in second grade before you learn fractions. For example, if you have two integers a and b, you can divide a by b, and you get a quotient, which is q, you get a remainder, which is r, and the crucial property is that the remainder is smaller than the divisor that you're using. And the absolute value sign here is here because we are considering negative numbers as well. To give you an example, if I divide 97 by negative 5, I'll get that the quotient is negative 15 and the remainder is 2. And 2 is less than the absolute value of negative 5. So this is the division with remainder. Next, we will talk about prime numbers. Well, I'll be a bit more pedantic here because we're talking about negative numbers. So I'll say that an integer is prime if its only divisors are 1, negative 1 itself, or negative itself. You need to remember this 1 and negative 1. It'll show up later. Yes. So to give you an example, negative 7 is prime because it can't be divided by anything other than that. Negative 33 is not prime because you can decompose it like that. Negative 1 times 3 times 11. And we know that for prime numbers, there is a theorem called the fundamental theorem of arithmetic, which says that every non-zero integer can be uniquely written as a product of 1, negative 1, and positive primes. And the positive here is important because it'll show up later. So how do you do this? Well, if it's a positive number, just decompose it. If it's a negative number, take the negative 1 out and then decompose it, right? So this is the theorem. So now we move on to the polynomials. Well, this is the long division that supposedly people learned in secondary school, I guess. So if you have two polynomials, f and g, you can divide f by g, and you get a quotient, which is q, and remainder, which is r. And the crucial property here is that the degree of r must be less than the degree of g. So it's because if we have the r is, if we have that this degree of r is somehow larger, we can keep dividing, right? So this tells us that the degree functions is somehow similar to the absolute value function. To give you an example, well, I did the math, so you don't really have to read this. Just believe me that the remainder is 6i, and because it's a constant, it is actually degree 0. So degree 0 is less than degree 1, which is gx here. That has degree 1, right? All right, so next we'll have prime factorization for polynomials, but we don't know what's a prime polynomial, so I'll define it for you. A polynomial is reducible, or you can just say it's prime if its only divisors are constants, and constant multiples of itself. Well, this sounds like negative 1 and negative 1 here, and positive itself and negative itself here. So that's kind of the connection that I'm trying to make here. To give you an example, x plus 1 is irreducible because you can't divide it by anything other than constant or constant multiples of itself. But 2x plus 2 is not irreducible. You can take out the 2, and then you have x squared plus 1, which is x plus I times x minus I, so that, x plus I divides this thing. So it's not irreducible. So we have, for complex polynomials, we have another theorem, which is called the fundamental theorem of algebra, which says that every complex polynomial of degree n has exactly n roots. But you can say it in another way, which is by saying that every non-zero complex polynomial can be uniquely written as a product of a constant and monic polynomials of the form x minus alpha. Monic here just means that the leading coefficient of the largest degree is 1. So how do you do this? Well, for example, for 2x plus 2, you take out the constant of the first degree, which is 2, take out a 2 there, and then you decompose it according to the roots of the polynomial. so for example, a polynomial having a root at alpha just means that it has a divisor of the form x minus alpha. So we actually have that x minus alpha, or yes? Okay, so we actually have that x minus alpha is the only form of irreducible polynomials for complex polynomials. So we have seen that you can do these two things, which is division with remainder and also prime factorization for both integers and polynomials. Well, this is actually an abstract theorem, and just to tell you a bit about the abstract theory, the integers and the polynomials are called the Euclidean domains, and so it's just a fancy name for where you can do division with remainder. And the operators absolute value and degree are examples of Euclidean functions that you define on somewhere you can do addition, subtraction, and multiplication. And so negative 1 and 1, and also the constants are examples of units in something called a ring, which is a more general thing than the Euclidean domains. And after defining all of this stuff, you can actually prove that every Euclidean domain has the unique factorization property, which is saying that every non-zero element can be decomposed as a product of primes, because you can also define primes in those areas. And I think I'll stop there, because do you guys want more? All right, because I technically have a bit more, which is because just now I talked about the fundamental theorem of algebra in the sort of pedantic decomposition way, but the normal way of thinking of polynomials is as a function over the complex plane.
Maybe you can push that to the discussion section, like afterwards, yeah.
All right, sure. So so you can see there's actually 3 sections. I just covered the first. So if you want, if you guys want more, we can continue later. Thank you.